we're going to show you proof that there's a brown dwarf off to the right of where Earth is. Earth is that yellow dot in the simulation. We're going to be looking at the left and the middle. First, I want you to look at the middle one. That's looking at Earth. Earth is going away from you, and north is to the top of the pie cut, and south is to the bottom. As the particles are leaving the sun, they are light blue, light green, and green. On the legend below, you can see that red is higher density, yellow is higher density than green and blue. But as these particles get out towards the edge of the simulation, a simulation that's fed by data, they go from green to yellow, from yellow to red, and from light blue to green. So they're gaining density the further they get away from the sun. They're supposed to be scattering and losing density, but they're not. They're gaining density the further they get away from the sun. That physically cannot happen unless, of course, there was a brown dwarf, let's say, off to the right there, about halfway up the pie cut. And every once in a while, you'll see the little dotted line, which is a magnetic field, or even the white line, go from north to south and south to north. It's waving around like a sock in the wind. And so this defies all laws of physics. If you know anything about physics, you shoot a shotgun. The further away from the shotgun you get, the more scattered the pellets become. Take a handful of rocks and throw them. The further away they go, the less dense they are, the more space between rocks. Well, in an instrument that's measuring density, what's going on? You look over on the left-hand side, and we're trying to see now the spiral itself, the circular spherical instrument on the left now. You look to the left of the left-hand spiral to see if the densities are increasing on that side of the spiral. And every once in a while you'll see an increase, but directly opposite the Earth and the Sun, they do not increase in density. Why? Because the wind is flowing in the same direction as the wind coming from the brown dwarf. We go to speed. Again, the middle pie cut, the dark red is your faster particles. As they get, especially the pulses, as they get further away from the sun, the slower they become. The further away particles get from the sun, the less gravity there is. And some of these are traveling at 400 kilometers a second. So some of these should be able to maintain their speed the further they get away. However, none of these particles, not a single one, is in fact gaining speed or maintaining speed. They're all slowing down at about the same region of the solar system that their densities suddenly increase as well. Go over to the left sphere now, and we're going to look at the spiral arms and see if, when it's opposite Earth and Sun, do they slow down? And we don't see the slowing. The red color in the spiral arm does not go away until the spiral arms whip around and get closer to Earth. Well, there's a brown dwarf off in the upper right, then that would explain why the speed decreases on the right-hand side of that spherical simulation, turning red into yellow. But then when it gets past that and goes in the same direction as the wind coming from the right-hand side of the simulation, that red in the spiral arm is maintained most of the time. So there's absolute proof then that something is slowing the particles down in one direction and increasing the densities in one direction. But yet on the other side of the sun, the speed is maintained, and the densities remain constant. Why? Because they're traveling in the same direction as Planet X. And so again, this simulation validates and verifies that we know where this brown dwarf is. And we think it's exiting the solar system, which is good news, but it's leaving its particles throughout the entire solar system. Those particles will not completely clear out till about 2023. And the background radiation is going to get rougher. The corona of the sun is going to get hotter over the next 2 years. So if you think the solar radiation is intense now, if you think the extreme ultraviolet is intense now, just wait for another year. We'll get a few more sunspots, and then we'll get a lot more X-rays. So I'm going through a lot of these instruments trying to figure out if we're accurate on where this brown dwarf is. As we become more in between, you should see more backside influence on this simulation. Earth is coming at you, sun is off to the right. So if particles are coming in from the upper left, you can sure see finally they're starting to back up the interplanetary magnetic field lines. They're starting to push back against the magnetic field created by the sun, and they're crossing Earth's magnetic fields. We look down on the solar systems. The Earth is traveling towards the bottom of your screen. Sun is off to your right. The brown dwarf then would be like where your left shoulder is, just about. But you could still see the effects of the electrons coming in. They're filling up the magnetosphere of Earth and then discharging into the tailstream, going in the direction of the solar wind. The ejections that we've been showing you year after year for the last couple years, some of those ejections have a nice V shape to them. The V point should be pointing at Earth, and the wide part of the V off to the left. Kind of like an arrow that's pointing to the right but yet traveling to the left. The electrons make like a ball or a sphere, and it's more round, and those eject as well into the tailstream. But they're not doing quite as much of that, and it appears that they're meeting a little bit of resistance. The spiraling is still there, but there's just not the degree of ejection, the speed of ejection that we're seeing, mainly because they're starting to meet resistance. If Earth was passing in between the brown dwarf and the sun, both stars were emitting particles, then the sun's particles would start running in opposition. That means the solar wind should be slower most of the time than it has been. We go to the Magnetosphere Simulation that measures energy, and you see that the compressions aren't as strong of the magnetosphere that they had been for the last couple months. The compressions were inside the 10 and 11. Those are Earth radiuses or radii, and you can see a presence of a backside energy in the tailstream. Now, there's two things that can cause backside energy: wraparound or focused particles that are passing through and then being focused towards where the zero is on the graph. That would create a large glow right center into the tailstream, and we see that from time to time. But we're also seeing second and third and even 4 levels of rings. Rings are created by electrons that are trapped. Notice how smooth the front side of Earth is and how much turbulence there is on the inner ring, the very inner ring, that light blue ring just outside the geosynchronous orbit of the satellite. becomes extremely distorted on the downwind side. Well, that's because that's where the resistance of the second sun is first being met. It's rippling through and around and along that inner circle, that closed inner circle. And you notice it becomes brighter again on the upper portion of the simulation and the actual backside of the simulation. So that tells me the particles are coming in from the upper left-hand corner. And if that were the case, then too, you would probably see favoritism towards the northern part of that tail stream. You would see more energy coming from a northern part of the tail stream. You would see less symmetry in that energy, and every once in a while you do see a greater collection of energy in the northern part of the tail stream. And every time the energy on the backside increases, the distance the magnetosphere is from the Earth increases. It's as if that energy on the backside of Earth is pushing against our magnetosphere. And the only thing that would do that with increased energy would be electrons coming from the left-hand side of the simulation. So they come in, they gather at the backside, and electrons repel one another, and our magnetosphere expands. But we always seen a constant presence. So we're scrolling through some of these instruments, and we're looking for some magnetosphere stuff, and we're looking for some solar wind stuff. But mainly I want to find the standoff position. The standoff position is the distance that the magnetosphere is from the Earth. And I have a little bit of a problem finding that instrument. It's on here when they move it around, but definitely I'm having issues. We go to some of the magnetosphere data, and remember we showed you pulses and pulses and pulses and a lot of turbulence happening. Well, look at that magnetogram. Tell me that all that scribble doesn't equal turbulence. But it all depends on what side of the sun and where you are in relationship to the sun's streams and the brown dwarf, Planet X, Nemesis, whatever you want to call it. So there it is. There it is. Click on it. There's a magnetosphere standoff. Click on it. Are you going to click on it? Oh, he doesn't see it. Oh, he saw it. He clicks. Well, there you see where the magnetosphere had been compressed and now is expanding up to from below 10 to above 12. When you get more electrons into your belts, you will expand your belts. So that's a good indicator that we're in electrons. Now I want to look at some of these magnetosphere simulations because some of them have been taken down, and if you look at the dates, you can tell if they're old or new. This looks like it's still new, but you can see the red and the blue are becoming offset. They were almost like overlapping one another and on top of one another. But as we get in between the brown dwarf and the sun, the electrons start competing, and therefore those peaks and valleys should be not simultaneous, but should be opposite of one another. Between the X and the Y component of our magnetic field, the X coming from the sun, the Y going out and coming to and leaving the Earth into the solar system, are starting to run opposite or transpose one another. That is a sign that we are becoming oppositional to that electron stream or to those electron pulses. So the other thing that I wanted to mention is an article that was given to me and referred to me was regarding the rings of Saturn. Now, we've showed you where the atmosphere, the northern vortex on the Saturn North Pole, used to be spherical, is now like a hexagon or octagon. I think it's a hexagon. And it's kind of shrunken down and slowed down. We know why. It's particle resistance from 10 times more particles in the solar system. The spot on Jupiter, as we've gone through several solar minimums, you can't blame this on a solar minimum, letting in all the interstellar cosmic rays. No, you can't do that, because last solar minimum and the solar minimum before that, the sunspots were just a tad bit higher, but they didn't allow so many cosmic rays into the solar system that it affected the size, the speed, and the shape of Jupiter's red spot. But we're seeing both resistance in that swirling red spot, which is a giant atmospheric cyclone on Jupiter, become smaller, slower, and higher altitude. That's like somebody taking a pottery wheel, putting a ball of clay in the middle, let the ball of clay spin, and then you compress with your hands that clay, and the clay begins to shrink, but the resistance slows down the wheel, and the altitude of that clay becomes elongated and taller. So we've seen that again when the wave that circles Venus every 20 days or so, there's a wave that goes, it's a V-shaped wave. It stalled out. People called it a standing gravity wave. I really don't think there's such a thing as a gravitational anything that's standing, but we proved it was just simply an atmospheric wave that had stalled out, just like a standing wave does in a river delta. When the tide comes in and the delta of the river flow goes out. So this phenomenon picked up in December, where the known focusing cone of helium was. Venus traveled through it, and a Japanese satellite found it, and they called it a standing gravity wave. And once again, all the explanations for these cosmic rays are laughable. But nonetheless, when we see Saturn, Jupiter, Venus's atmospheres all responding to resistance, it's just a matter of time before the rings that are traveling around Saturn become compressed and slowed.